the contractile process of muscle operates, I always want you to be thinking about 4 processes. It's always nice to put things in a box and be able to kind of partition them out. And those 4 fundamental processes are excitation. Excitation, you can see up here, I've written as an electrical event. You could write electrophysiological event. There's excitation, contraction, coupling. Now you are all experts on transduction. You would all tell me that transduction is defined as a process by which a external signal produces some type of intracellular response. There's a contractile process itself, which we started to go through last Wednesday night. And really, the way to be thinking about that process is to be thinking about the so-called cross-bridge cycle. As I stated to you last week, the myosin molecule, each myosin molecule is a force generator, and it's going to go through this cyclic attachment, power stroke, detachment, as long as 2 things are present. Calcium is the on switch, and then we got to have sufficient amount of ATP to ensure that we can go through the cross-bridge cycle over and over and over. Tonight, we're going to get into relaxation. And relaxation is nothing more than a recapitulation of everything I've shown you up to this point. It's really turning off excitation. It's turning off EC coupling. It's turning off the molecular motor. So we get into that. Then I'm going to describe for you the different types of molecular motors, because it turns out that there are slow molecular motors and there are fast molecular motors. And when you sit there and watch the premier competition in the world, which is called the Olympics, and you sit there and you can see people who can run 100 meters in 9.6, I believe, if you go take a look at Usain Bolt. If you follow track, you know that Usain Bolt's the fastest human to ever live, incredibly fast. So there are people who can run very, very fast. How they do that? They got fast molecular motors. There are other people who cannot run as fast, but they can run for very long periods of time at a very high intensity. And I think I mentioned to you this individual, Jakob Ingebrigtsen, over in Scandinavia. Go watch his YouTube videos. He's phenomenal to watch. But he's a incredible endurance athlete. But I'll assure you that he doesn't have as many fast twitch fibers as the sprinters do. But it turns out Jakob Ingebrigtsen is pretty fast. He can run pretty quick. We've already talked about the structure of sarcomeres. So once I get done talking about relaxation, we're going to talk about the different types of molecular motors. I'm going to describe for you the structure of the myosin molecule. And then we're going to talk about what happens to the Z line, the A band, the I band, the H zone when a contraction takes place. And there's this model called the sliding filament model. It's not just a model. It is, in fact, a fact. Is that our thin and thick filaments slide past one another. That's how the sarcomere shortens. So I'll talk about that. I don't know if I'm going to get into muscle mechanics tonight, but we'll see how far we get. So that's it. That's kind of the outline for tonight. What number did I leave off with last week on the cross-bridge cycle? Was it like 23? Okay, great. All right, so now we're in that last box. Relaxation. Now please appreciate there's all different types of contractions. There are contractions where the muscle stays in a contracted state for a relatively long period of time. For instance, if I came along and I simply tried to lift up on this desk, I could sit here and I'm trying to lift up, I'm still trying to lift up, I'm still trying to lift up, and my muscle's on. It's still on, still on, still on. And I could sit here trying to do this for maybe a couple minutes or maybe even longer. So there's no cyclic activity. And in the instance I just tried to represent, there, the motor neuron is firing continuously. Calcium is being released continuously. That's causing tropomyosin to rotate, to stay in that state where it keeps the myosin binding sites uncovered for as long as I've got that muscle on. And my cross bridges are attaching, detaching, attaching, detaching. But that's for a contraction where the contraction is a relatively long duration. But when we do stuff like this cyclic activity, which is called a gait cycle, where we sit there and take a look at the on-off state of our muscles in our leg, upper leg and lower leg, those muscles are going through cyclic phases of all four stages. We're exciting the muscle, we've got EC coupling, we're turning on the molecular motor, then the muscle's got to relax so that we can reset the muscle, we can re-lengthen it, and we can go through this process over and over and over again. So, how does that happen? Well, what I'm showing you is here, if you can see in the back, I've drawn the tropomyosin so that it has uncovered the myosin binding sites. So our molecular motors are on, but how do we turn them off? And the off part starts up here. So here's our alpha motor neuron. Let me just show the presence of ACH. So we've got to turn off that alpha motor neuron. So that's going to be step 24, correct? Is that correct? In other words, our alpha motor neuron is repolarizing and it's off now. It's no longer releasing acetylcholine into the neuromuscular junction. But we still have ACH bound to the acetylcholine receptor. And as long as ACH is bound to those two alpha subunits, that ion channel is going to be open, causing depolarization. So what we've got to do is we've got to get rid of the acetylcholine that's bound to the ACH receptor. And within the synaptic cleft, there is an enzyme. And I'm just going to put capital A, capital C, lowercase h, capital E. That stands for acetylcholine esterase. And it breaks down the molecule of acetylcholine. So now we have removed acetylcholine from the alpha subunits. That then causes the ion channel of the acetylcholine receptor to close. So coming back here, oops, I didn't put my number here. So number 24 is turning off the alpha motor neuron. Number 25 is we're going to remove ACH from the alpha subunits. Of the acetylcholine receptor. That then causes the ion channel to close. So we've got our ion channel closed. That then leads to repolarization of the sarcolemma. That's number 27. And of course, make sure you understand that the membrane of the T-tubule is nothing more than an extension of the sarcolemma with one exception. The membrane of the T-tubule, the sarcolemma, also has voltage-gated calcium ion channels in it. So I'm going to put number 28. Repolarization of the T-tubule membrane. Maria. Maria, Maria, Maria. What's going to happen next?
The conformation of the protein linker.
Which one are we talking about?
The one that's attached to the voltage-gated calcium channel.
Okay. Is there something that'll happen before that? Take a look at what I wrote here, number 28. Repolarization of the T-tubule membrane. So what's going to happen? Don't you look at her, Maria.
Well, it's gonna close.
Close a what? Shh. Silence over there.
I don't know. I'm confused.
Anybody gonna help Maria out?
The voltage gated sodium ion channels closed.
Calcium?
Okay, so we've got repolarization though of the T-tubule membrane, so by definition, the voltage-gated sodium ion channel is closed. The voltage-gated potassium ion channel closes. Help me out here, folks. The voltage-gated calcium ion channel is going to close.
Okay.
So number 29.
VG that connects the linker because it's open.
Closure of the voltage-gated calcium ion channel. Maria, Maria. Anybody, there's a song that's got that in it. Anybody know who sings that? That's like Mick Jagger, right? He sings Maria, Maria. You guys ain't know who Mick Jagger is. That's the Beatles, right?
I think
Huh?
it's Carlos Santana.
Oh, very
and-
good. Excellent. Yeah, very good. Santana. All right, so Maria, we have these voltage-gated calcium ion channels closed. Now, do you want to say what you just said a few moments ago?
Yes, that's gonna change the structure of the linker protein.
Right.
And then so calcium release channels are gonna close.
2 thumbs up, very good. So the closure of the calcium release channels. Where's Jocelyn? I want to talk to Jocelyn. Jocelyn, it's really funny how I've asked her a question, now I'm asking you a question. I'm not sure what the rhyme and reason is there, but I'm sure there is some logic behind it. Miss Jocelyn. Those calcium release channels go by a different name. What is that? I can see Michael shaking his boots because he can see that he's next.
I really don't know how to pronounce it, but I have in my notes ryanodine receptors.
Say louder.
Ryanodine receptors.
Ryanodine receptors, that's right, very good, excellent. Okay, so we've got these calcium release channels that close, and number 31. We still have calcium bound to our troponin C. That's our on switch, right? That's what's controlling the position of tropomyosin, is the presence or absence of calcium bound to tropin C. Guy, I'm thinking of a name here. There's an instant in class here. Goes by the name of Maria. What do we have to do to turn this thing off, Miss Maria? It's just an extension of what I was just talking about. She's going, what? I didn't even hear it.
Does it have to be with calcium bound to TNC?
Okay, well, what about it? Mr. Vargas, what would you say?
We have to get rid of calcium.
That's exactly right. We do have to get rid of calcium. How are we going to do that? We've stopped releasing calcium, but now we've got to get rid of that calcium. How do we do that?
Would it go back into the calcium ATPase pump?
That's exactly right. Our calcium ATPase pumps are going to suck that calcium back into the SR. That's exactly right. So we're going to come up here at number 31. We're going to put sequestration. Ooh, big word, sequestration. I feel like I'm in law school. Mr. Landon, what does that word sequestration mean?
I'm not too sure.
No? Anybody, what does sequestration mean?
To take?
Not bad. How about to hide away? Juries are sequestered. What that means is that once the juries are out of the courtroom, they are hidden away so that they're not hearing all the media and all the hearsay, nonsense, social media. They basically are naive to what's going on out there in the social universe, and they're just tuned into the facts of the case without any poisoning, so to speak, of their perspective. Sequestration. That was good. That was real good. Sequestration of calcium. So we're pumping calcium back into the sarcoplasmic reticulum. That causes calcium to dissociate from troponin C. And now, number 32, So I'm going to put sequestration calcium. So number 32 is the removal of calcium from troponin C. Number 33. Tropomyosin covers myosin binding sites. Ms. Jocelyn, what's going to happen to force production? You could say it's going to stop, but a different way I'm going to put it is it's going to decay. Here I'm going to put force decay. And Jocelyn, you're going to give me another word for that that starts with an R and ends with an N. What's that word? No, it's not repolarization. Anybody?
Relaxation.
Yes, relaxation. That's exactly right. That's the name of this box right here, right? Here in parentheses, I'm going to put relaxation. So as I said, this relaxation box has got a lot of things in it because really what it is it's just a reversal of all the things that led up to turning on the contractile apparatus. Questions about that? Don't be bashful. All right, I'm going to erase everything over here on the board left. Is everybody good with that? Okay, so what I'll show here, imagine over here, down here, and below here. Everybody with me? All you're going to do is just take this image here, put another image over here, except on this image, I'm just going to show you the orientation. I'm just showing one of those, just to show you how these are going to go through their power stroke and come in. And one of the points that I want to make, and I'm not sure that I did this in thinking back on lecture last week, but that power stroke, there are two mechanical phenomena that are occurring. The head of the myosin molecule is producing force, and it can cause changes in the length of the muscle or muscle fiber. So during a power stroke, you're going to tell me two things are happening: force production, change in length. Now, what I'm showing up here in this box, imagine 500 of those things. If I sat here and tried to draw that tonight, we probably would be here for probably a couple hours, just me drawing it. But imagine that within each thick filament, there are 500 molecular motors. There's a boatload. So I'm just going to bring or show you the structure of, actually, let me do the other one here. We're just going to focus on this one here. So just an enlargement. And so when we sit there and take a look at a myosin molecule, there's what is known as a myosin heavy chain. And this myosin heavy chain has two parts to it. If everybody will just look up here, what I'm showing you here in terms of this oscillation, what I want you to imagine is to think of a corkscrew type of structure. And Mr. Corey is going to tell us that when we think of that corkscrew structure, and we're in protein land, and we think about primary structures, secondary structures, and tertiary structure, this corkscrew structure is referred to as what? That's exactly right. Thumbs up. That's exactly right. So that corkscrew-like structure, that coil-like structure is referred to as an alpha helix. And this part of this so-called myosin heavy chain is known as the rod region. And the rod region is it contains purely structural information. So just time out. So what do I mean when I'm talking about structural information? If you see the way I've packaged these three different myosin heavy chains, it's that rod region that allows for this alignment between multiple myosin heavy chain molecules. That's structural information. It's all based upon the rod region. So the packing of these myosin heavy chains is due to the information stored within this rod region. And that's purely a structural region. There's this region up here. And this is known as the globular head. This part, if everybody will look up at the board, if everybody just, all eyes up here, this part right here is this part that I'm representing here, is analogous to this. This is kind of like the ore, if you will. What's the globular head? This is where the molecular motor is. Again, all eyes up here. So it's this region that goes through the power stroke. Let's see here. Oh yes, another person. Mandy. Where's Mandy? Mandy, we need to have a discussion. How do I get, so here's the head of my myosin molecule, the globular head, it goes through its power stroke. How do I get it back over to here? Do me a favor, everybody, look at your notes from last Wednesday night. And Mandy, you lead the discussion on this. If you can't figure it out, then you can pass off to Elizabeth.
Is it hydrology?
Of? That's exactly right. Because when we hydrolyze the ATP, we break the ATP down into ADP plus phosphate plus what, Mandy? I can't hear you.
Water.
No, still can't hear you. I think it starts with an E and ends with a Y.
Oh, energy.
Ah, energy. That's why we are breaking off that third phosphate. We're trying to get the energy out of that ATP molecule. And this is the energized position. This is the de-energized position. How do we get back to the energized position? By taking the energy away from a molecule of ATP. So here I'm just going to write energized. And over here I'm going to write de-energized. Okay, so the globular head is a molecular motor. But there are regions of the globular head that have incredible functional importance. The first is that there's a part of the globular head that binds to, what's the name of this? Miss Maria, what's the name of that little black dot there? What's that called? The myosin what? The myosin binding site. What binds to the myosin binding site? The globular head of the myosin molecule. So here we're going to put binds to the myosin binding site of actin. Two, we know that there's an ATP binding site located in the globular head. Three, write this in your notes. The myosin molecule is a actin-activated ATPase. Ms. Kaylee, what are ACEs?
Oh, ACEs are enzymes or
That's right, they're enzymes
And they
that
break down.
speed up
They're
chemical
catalysts.
reactions. So within the globular head resides the ATPase activity of the myosin molecule. I'm just going to put enzymatic properties. And you're going to understand that what I mean by enzymatic properties is that's where the ATPase activity of this myosin molecule resides. It resides there in the globular head, which is exactly where it should, right? If it's the globular head that's binding to actin, then it makes sense that that should be the region, the place where we're actually hydrolyzing the ATP. And as it turns out, there are two proteins that are bound to the globular head that have functional importance. So here in purple, we're going to say that we have a so-called regulatory myosin light chain that is bound to the globular head. Mr. Bennett, have you ever done electrophoresis?
Yeah, high school.
Oh, in high school. All right. All right. So when we talk about light chain versus heavy chain, what would that mean in electrophoresis land? If you guys don't know what electrophoresis is, it's a very fundamental technique, but incredibly powerful. Really, really powerful technique where you run proteins through a gel, and I'm not going to go any further. So no? Anybody in here done electrophoresis? Go for it.
Does it have to do with how big the protein is and like how far it's going to stretch out?
That's exactly right. So proteins are relatively small. They have less friction moving through the gel, whereas bigger proteins have more friction. And so what happens is these proteins will make like little lines in your gel. Very, very powerful technique. Probably one of the most fundamental techniques in the modern day biology lab. So why do we call this a heavy chain? And the answer is simple, because it's a large protein. Why do we call this a myosin light chain? And following up on this theme, it's because this is a relatively small protein. Very important word there, regulatory. Regulatory to me sounds like things that affect how things work. We'll come back to that later. And then we've got another protein. And this is referred to as a so-called essential myosin light chain. Coming back in this diagram, myosin heavy chain. Our acronym for this is capital M, capital H, capital C, myosin heavy chain. Over here, we're going to put MLC. So you talk about a regulatory MLC or a regulatory myosin light chain. Here, for the essential myosin light chain, again, we're just going to use those initials MLC, and you sit there and say, yeah, I'm talking about the essential myosin light chains. Let me stop and ask, are there any questions? Anybody needs some clarification? Don't be bashful, speak up. Yes, go for it.
So, for on the left side of the image, we have 3 myosin heavy chains that are stacked on top of each other due to the structure they have. And that's,
So we can't have all 3 of them in the same spot,
no.
right? So we've got to have them kind of spaced out down along the length of this. And the part of the myosin heavy chain that's responsible for that spacing is the rod region.
Oh, okay. So there's no such thing as like MHC1, MHC2 to like differentiate between like the one that's most to the left and most to the right? It's just like,
No.
no? Okay.
No. That's a good question. Sit there and think about that, yeah. All right. Let me come along and put in a mirror image. Sorry, the back of the purple and the black look the same, but I'll try to do better next time on that. What I've just drawn is what's referred to as a myosin molecule. It's a misnomer. I don't like calling this the myosin molecule because molecule is singular and the structure I've drawn up there is not singular. It's very plural. But the myosin molecule is referred to as a hexamer. So this whole thing that I've drawn is called a hexamer. There are 2 myosin heavy chains. There are 2 regulatory myosin light chains, and there are 2 essential myosin light chains. And you add that up, you get the number 6, hence the use of the term hexamer. But understand that when we talk about the myosin molecule, we're talking about the hexamer. When we talk about a myosin heavy chain, we're talking about, in this case here, the solid red. Or I could be talking about the dashed red, but that's each of those is an independent myosin heavy chain. Questions about that? Any confusion? Let me put something up you saw last week. Here's actin and myosin, and bound to the myosin is ADP and phosphate. This is the cross-bridge cycle. So in the presence of calcium, myosin will bind to the myosin binding site in actin. This is our attached state. And then, very rapidly, we have the release of phosphate, so that we've got actin, bound to the actin is myosin, and bound to the myosin is ADP. The phosphate has been released. This is our power stroke. Now, I'm not going to write out the rest of the scheme. The rest of the scheme you should have in your notes. But there are different types of myosin heavy chains. There are slow types of myosin heavy chains and there are fast types of myosin heavy chains. What do we mean by that? Well, if you can imagine the rate at which we can go through this cross-bridge cycle is fast when we have a fast myosin heavy chain. When we have a slow myosin heavy chain, we go through the cross-bridge cycle at a slower rate. Yes, sir?
Is that what the whole slow twitch versus fast
It
twitch
is.
muscle
That's
is?
exactly right. It's all due to the type of molecular motor. That's where I'm headed. Is for you to understand that we talk about fast twitch and slow twitch. It's dependent upon the type of molecular motor we have. That's what causes these effects. So, simple question. If we can go through the cross-bridge cycle at a really fast rate, then what will force production be for that particular myosin heavy chain? Will we cause force production to go up very rapidly, or will it go up slowly? It's a rhetorical question. All of you should get the answer, and the answer is rapidly. If we have a slow type of myosin heavy chain, force production is going to go up at a slower rate. If we have a fast type of myosin heavy chain, we're going to produce length changes faster. The muscle will be able to shorten at a faster speed than if we have a slow molecular motor. So the type of molecular motor that we have is incredibly important for muscle function. It determines the rate of force production. It determines the rate at which the muscle can contract. Everybody with me on that? Have I confused anybody with that? Don't be bashful. Go for it.
It's not really confusion, just a clarification. So it's dependent on the type of motor head that it has, not on any other component.
Type of myosin heavy chain that we have. So,
Heavy
and
chain.
that property we're talking about resides within the globular head,
Okay.
right? Because you're going to tell me that the globular head has got, oh, and I forgot to write down number 4 here. I think I forgot. Let's see. Yeah, I did. All right, so I'm going to describe the types of molecular motors. Remember, it's the myosin heavy chain that is the business end of this molecule. It's the myosin heavy chain that's responsible for the mechanical properties of muscle. So here we're going to talk about the types of MHC. And Mr. Corey, when we have a type of a protein, but there are multiple forms of that protein, we call that what?
Oh, I want to say, not an isomer.
Yes, that's what I was saying, isoform. That's exactly right. So isoform is just a slight modification of a particular type of protein. So types of myosin heavy chain isoforms. The first type is referred to as a slow type 1 MHC isoform. Andrew, where's Andrew?
Yes.
Andrew, so you're gonna tell me that for this type of a molecular motor, it goes through its cross-screw cycle, goes through it at a slow rate, right? And therefore, it produces force at a relatively slow rate. It produces shortening at a relatively slow rate. Ah, I forgot, why did I forget that? There's a so-called fast type 2A MHC isoform. Well, taking what Andrew said, you'd sit there and say that this fast type of myosin heavy chain goes through the cross-screw cycle at a faster rate compared to the slow type 1. There's another type of fast MHC isoform. This is called the fast type 2X myosin heavy chain isoform. Sorry, I don't get to make up the terminology because you look at this and just go, where is the rhyme and reason? I see a rhyme and a reason between type 1, type 2, but how do I get from 2A to 2X? That's bizarre. The way I think about it is Planet X. What the hell is Planet X? Anybody? Planet X is a hypothesized planet that lies beyond Pluto, but nobody's ever seen it. They just hypothesize that it's out there. They call it Planet X. Well, I think in muscle biology, when they found this isoform, they go, hey, is that a real isoform or is it not? Is it something else? They gave it Planet X name. The next type is fast type 2B myosin heavy chain isoform. And what I've done is I've written these with regards to the speed of their cross-screw cycle. And here we're going from the slowest to the fastest. And in each and every one of us in this room, we have varying proportions of the slow type 1, the fast type 2A, and the fast type 2X. Okay, you can see there I put large mammals. So if we're talking about like elephants, giraffes, humans, those are the types of myosin heavy chain isoforms expressed in our muscles. If we're talking about small mammals have got the slow type 1, the fast 2A, the fast 2X, and the fast 2B. Those are mammals. Test question for all of you. Here's a simple motor task. To sit there and take your finger and be able to tap as fast as you can with your finger. What do you think? How many times can you tap with your finger? How many times per second? 1,000 times a second? 100 times a second?
3 to 5 maybe.
That's a good guess. That's a real good guess. Let's just say around 4 times a second. So I can turn on and turn off my muscles 4 times a second to get this oscillatory effect. I know all of you have seen an amazing animal, doesn't fall into the mammal category, but hummingbirds. Hummingbirds are amazing. You know, I watch hawks and I can see them flap their wings. I watch those stupid crows, those blackbirds, I can see them flapping. How many of you can actually see a hummingbird flapping its wings? I sure as heck can't. And so get your wings out. Come on, get your wings out. And how many of you in here can flap your wings 100 times a second? Because that's what they can do. Just sit there and think about it. I was just thinking about that, and I dislocated my shoulder. What do you think? Do they have fast muscles or slow muscles or pectoral muscles? They are on, off so fast, it's incredible. Really incredible. Go watch little mice scamper around. You're a mouse, guess what? You're subject to predation. Humans aren't really, if you sit there and think about it. There aren't, at least in civilization, there aren't apex predators that we come in contact with on a daily basis. But if you're a little mouse or a little rat, man, gotta be able to generate very high gate frequencies to get from point A to point B without some little bird coming down snatching you away. So anyways, these are our different types of molecular motors. Now, in skeletal muscle, the regulatory myosin light chain and the essential light chains are not important. So why the heck did I put that up there? Because we're going to be transitioning on over to smooth muscle. And smooth muscle, what you're going to find out is that it's the phosphorylation of that regulatory myosin light chain that is important. And how do we phosphorylate molecules? Ms. Jocelyn, how do we phosphorylate molecules? That's exactly right. How do we dephosphorylate a molecule? Oh, you're going to find out. So that's how our smooth muscles are controlled, is through the phosphorylation and dephosphorylation of the regulatory myosin light chain. So the point I'm getting at is in skeletal muscle, that regulatory myosin light chain is not important, but man, when we get to smooth muscle, that's the control, the phosphorylation of it. And those darn little alpha and beta adrenergic receptors, whew, if you go back and look at your M1 or alpha 1, I forget, alpha 1 adrenergic receptor, how does that work? Anybody going to help me out here? Let's see here. Sarah Wu. Where's Sarah? Sarah, can you help us out here? How does that alpha 1 adrenergic receptor work? She's going, oh my goodness, I can't believe I forgot that already. Are you raising your hand? Kind of looked like it. You were a good senator going. Elizabeth Stone. Go for it.
It uses a PLC to make IP3, and there's the G protein as well. So the receptor acts on the G protein, which acts on PLC, turns the PIP2 to the IP3.
Hey, what does that IP3 do?
It will work on the endoplasmic reticulum, and calcium will come out.
Calcium, and what's gonna bind to calcium?
Calmodulin
And what does calmodulin do when calcium's bound to it?
activates an inactive protein kinase.
Interesting. A myosin light chain kinase. That's where we're heading, that's where. And that's the beauty of this class, is that one thing feeds into another. All right, let's talk about our sarcomere again. So here's our Z line. Here's the opposing Z line. Attached to the Z line is the thin filament. I'm just going to represent the thin filament via the presence of the actin filament. These little green circles that are attached in series to one another. And then we've got, so I'm just going to put here, make sure you understand the difference between the thick and the thin filament, but for our purposes, we're just going to say that that represents the thin filament, even though that's not strictly correct. And then we've got the thick filament. All right, so we've got the Z line. That was impressive, actually. So this space between the end of the thick filament on over to the Z line, we're going to call the I band, even though it's half of the I band. But for our purposes, this will work. We have the A band. The A band is simply the length of the thick filament. And then we've got this gap between the two opposing thin filaments. And that's this distance here. This is our so-called H zone. Then we're going to make a table. And in this table, in our far left-hand column, we're going to put type of contraction. In the next column, we're going to put width of the I-band. Next column, we're going to put the width of the Z-line. Next column, we're going to put the width of the A-band. And in the last column, we're going to put the width of the H zone. I'm trying to stay color coordinated here, but I guess I'm coordinated with over there. Okay, so width of H zone. We're going to talk about three different types of contractions. The first is a so-called isometric contraction. Isometric. Well, the prefix iso means same. Metros, M-E-T-R-O-S, length. Same length. So if I come along and I contract my muscle against an immovable object, my muscle's on, but is my muscle shortening? It's not. So what's happening then to the width of the I-band? If my muscle's not shortening, by definition, the individual sarcomeres that make up the muscle are not shortening. And therefore, you would tell me that the I-band gets longer, gets shorter, or doesn't change? Doesn't change, right? The Z-line. Here's the way I want you to think about the Z-line. The Z-line is this wall right here. And just to really try to solidify what I'm talking about, we're going to say that this wall is made out of concrete. And it's on rollers. The wall can be moved towards me. The wall can be pushed away from me. Everybody with me on that? So the wall is going to be our Z-line. I have a rope attached to that to the Z-line. The rope represents the thin filament. My hands attached to the rope. What do my hands represent? Thick filament, but what part of the thick filament? The molecular motor, right? And so I'm going to grab a hold of that thin filament and I'm going to pull. And you tell me that that wall would come towards me. Alternatively, it could be pushed away from me. So the point I'm getting at is that the point we want to think about is that these are non-deformable. We can't make the I-band thicker. We can't make it thinner. It's like a fixed point of fixation that's, you cannot change its dimensions. Everybody with me? So no matter what type of contraction, the Z-line always has the same width. So coming back to that point, you would tell me that during isometric contraction, the Z-line doesn't change. Andrew, coming back to you, what happens to the width of the A-band?
Wouldn't the A-band be the same for everything?
There will be, right? No change. And if we're talking about the H zone, the answer is the same, no change. So that part's easy. The next type of contraction we're going to refer to as a shortening contraction. The other term that's used to describe a shortening contraction is referred to as a concentric contraction. As somebody who studied muscle mechanics for 50 years, I don't like that term. I like the term shortening because if I sit there and talk about a shortening contraction, I'm hoping you're envisioning looking at the sarcomere up there and you go, oh, it's getting it shorter. Versus if I go concentric, you might be sitting there going, I've never even heard of that word, concentric. I don't know what that word means. All right, coming back to you, Andrew. You're going to tell us that during a shortening contraction, what's going to happen to the length of the I-band? It will shorten, that's right. And I love that song by Santana. That's a great song. And I don't even know what it is. But it does have a pretty name to it, Maria. So, Maria, what's going to happen to the width of that Z-line?
It's gonna stay the same.
It is going to stay the same. Very good. The width of the A-band, Mr. Bennett, what are you going to tell me?
I would say that it stays the same as well.
It does stay the same. That's exactly right. Tyler, what are you going to tell me happens to the width of the H zone?
Shortens.
Thumbs up. Very good. Excellent. You guys are rocking it. All right, and then we've got so-called lengthening contractions. The term that's used to describe lengthening contractions often is you'll see the word eccentric. Do not like that word. That's a very arcane term. Versus when I tell you that your muscle's undergoing a lengthening contraction, hopefully all of you would sit there and say, each of the sarcomeres has to be getting longer. Now, some of you might say, well, how do you create a lengthening contraction? I don't get that. Well, I've got some groceries, and I come along and I lift them up from the ground, and I put them here. My muscle right now is on what type of contraction? Concentric, eccentric, or isometric? Hopefully all you tell me isometric because my muscle's on, but it's not changing its length, right now. I come along and now I lower it down. My muscle's on the entire time I lower it. What's happening to the muscle fibers?
Lengthening.
They're getting longer, right? So something that you pick up where you lower it rather than dropping it. If I dropped it, that's different. But if I'm lowering it in a controlled fashion, that's an eccentric contraction. Don't know how many of you in here are skiers. Back in my days, that was a very, very popular activity. But you sit there and think about going skiing, and as you go over a hill, you tend to flex your leg. And when you do that, your quadriceps are still active. But as you go down here, you're lengthening. That's a lengthening contraction of the quadriceps. All right. So what happens to the I band? Elizabeth, you're up to bat. What happens to the I band during a lengthening contraction?
It gets longer.
Yeah, we're just gonna, even if you didn't understand what's going on, you just sit there and take the opposite of what you see here, right? So you sit there and say that the I band is gonna get longer. The width of our Z line is never changing. Come to find out, the width of our A band never changes. And in this case, the H zone is lengthened. Okay, just need one last 30 seconds. I'll come back to this on Wednesday night. But what's happening is the length of the thick filament never changes. The length of our thin filaments never change. They're simply sliding past one another due to the activity of our molecular motors. And so our modern day mechanism by which muscles contract or lengthen is the lengths of our thick and thin filaments do not change. It's simply that they are sliding, these filaments are sliding past one another due to the attachment or detachment of our molecular motors. That's the sliding filament model. All right, so I went over a little bit. I'll see you guys back here Wednesday night. If you have questions, comments, come on up. I'm more than happy to try to help answer those.